So I'm Dave Rowland. I'm the CTO of the Audio Squadron Group. We have two main sides to our business. On the Prism Sound side, we make high-quality audio interfaces and converters for large studios. And then on the Traction side, we do a lot of software. We make some really in-depth, detailed synthesizers, and then a DAW or DAW waveform and the Traction engine, which is open source, which it runs on. So first up, quick riddle. When is a door not a door? When it's a jar? Is that too meta? Make more sense now? Okay, right, enough of the fun, serious stuff from now on. So I'm going to start with a quote from Lex Dromgoole, who's the CEO of Bronze, which is a kind of an upcoming AI machine learning powered DAW. He states, "I can see why no one in their right mind would undertake building a DAW." And that kind of sets the tone for what we're going to talk about today. This actually comes from an article that was doing the rounds a few months ago from DJ Mag called "What is the Future of the DAW?" Can I just have a quick show of hands? Who's read this? Good. Yeah, quite a few people. So we'll be drawing inspiration from this over the duration of the talk. So Lex goes on to say, if you add the fact that people can't really make any money out of it because it takes so long to develop, you can see why there's no innovation. I think that's actually a big part of it. The economic incentives aren't there. And that's really what we're going to talk about today, is why does it take so long, and therefore why are the economics incentives not there? So I read through this article and tried to pull out some of the key terms that were kind of prevalent to building DAWs. And I came up with this word cloud, and you can see at the core here we have stability and dependability. DAWs are mission-critical pieces of software. People rely on them, professionals rely on them to get their jobs done. And kind of strengthening that, we have terms like sacred space, muscle memory, sac-to-sanc keyboard shortcuts. People need to use these tools without thinking about them and just know that they're in the zone being productive. Then we have engineers, producers, and artists, all very different types of users, but still using the same tool. So perhaps it's not tailored for each of those very different tasks and professionals. And then we have the more negative terms like roadblocks, exasperated, frustrated, no innovation. You know, these are the things that people don't like about DAWs and perhaps feel they could be done better. There's another quote in this article from our very own Joshua Hodge from the Audio Programmer. And he states, "I feel like it's hit a plateau in terms of creativity, and where a lot of people are just creating the same thing. A lot of people are wondering, what is the next thing? What is it going to look like? And how can we expand on the current capability of what we're doing with the DAW? But I don't think anyone has quite nailed what it will look like." And that is quite sort of prevalent. It echoes the fact that we're perhaps at this tipping point where there needs to be a bit of a paradigm shift. So I'm going to go back to the beginning of DAWs and the tasks that they do. And they're effectively created to replace analog studios. So all the tasks that you do in an analog studio have kind of digital equivalent. Do recording, arrangement, playback, exporting and bouncing, file management used to replace all those analog tapes. And pretty soon afterwards, plugins came along, and they were used to augment features of the DAW or DAW to provide functionality like synths, effects, and MIDI generators. And the DAWs liked this kind of plugin model because they had a very thin API, and that to some extent sandbox what they can and can't do. So you often see DAWs with their internal plugins that are really part of the DAW, but presented as plugins for their own synths and effects. And then the plugins over time wanted to add more functionality, so they wanted to get more of what the DAW has. So you have things like Pro Tools Audio Suite for reading and writing audio files, Melodyne ARA for kind of intercepting audio clips and regions for within the DAW, and then a whole bunch of extensions from Reaper, Presonus, amongst others, that enable you to get at specific pieces of information within the DAW. So over time, really, the two have come together. And when you want to build something that is both a plugin and a DAW, you end up with an app, and an app that does all of these things is really just a DAW. So I'm going to reiterate that quote from Lex that we heard. If you add the fact that people can't really make any money out of it because it takes so long to develop, you can see why there's no innovation. That's actually a big part of it. the economic incentives aren't there. So we're going to nail down on the economic incentives here. This next part is going to be quite quick, but there's a lot to get through, and hopefully it imparts the complexity that we're talking about. So you can imagine product designers get together and then create a bunch of user stories in the agile world. So you get a bunch of features, things like, user stories, like I want to be able to arrange multiple audio files on a timeline, and if you summarize that in this list, that effectively becomes arrangement. So your product is a whole bunch of user stories that basically cover all of these features that DAWs do. So we're going to try and quantify the costs of building something that is effectively a DAW. So to do this, I went to Glassdoor and looked at the average salary for a senior software engineer in the audio industry. This came out to nearly 73K, which averages out about £300 a day or $375. And a quick note, when I do these estimates, these include doing things properly, right? Writing tests and validation, because this is mission-critical software. It needs to be stable, needs to be dependable. We want to do things properly. And we're going to have a running totalizer in the top right to see how much doing things is going to cost us. Okay, first, the simple stuff. We need a notion of time, right? Digital audio systems are time, and the natural time in digital is samples. That's not particularly useful. In the real world, we tend to talk about things in terms of time in seconds, but we have a nice sample rate that can convert between those two and a simple equation that can do that for us. There's a more musical way of talking about time, though, and that's in terms of beats, and we use the tempo to convert between those two. We have a nice simple equation to do that, and it can be rearranged as well to find the beats if you've got a tempo and some time. And there's kind of one higher level concept of musical time, which is bars and beats, and I'm kind of glossing over a few complexities with the denominator here, but effectively your numerator of your time signature gives you the number of bars. So how long is it going to take to do this? Well, if you're really good, have a good idea of these concepts, then a couple of days, write some tests, you got some classes, and away you go. But it's not usually that simple, because in most modern applications, you have dynamic tempo. And that's either because you have a way of programming in a dynamic tempo with ramps and curves and changing time signatures, or you're chasing to some external source. It could be MIDI clock, it could be Ableton Link, that kind of thing. But effectively, tempo can change. You need to support that. Now, I'm not going to go into all the technical details, but the rough way you do this, if you've got ramps and curves, is you can chop those up into small sections, figure out what the current state of your time is, so the bar number, the number of beats elapsed, the time, and then use that state to do some linear equations on the end. This is what the code to construct that sequence from a high-level sequence of tempo changes in our Traction Engine code base looks like. Of course, there's curves, so we need some Bezier calculations in there, and then once we've got that, we have some calculations that can do our conversions between the two. So building that, if you're good, a couple of weeks. Okay, we spent about 5K, but it's probably going to take a bit longer than that, to be honest. Okay, we've got a notion of time. Let's do something proper. Audio file reading. What are the problems with audio file reading? It's simple, right? Well, it's not like we're making a player here like Spotify or Apple Music or something. We typically in a DAW have many files. They could be hundreds along a track or many tracks. And also long files. Imagine you're recording a podcast or an orchestra or something, or a gig, several hours. Then we have the fact that the transport position, particularly when editing, can jump around. We've got loops and editing positions that will change, and we need to work around all those clicks. Then we have clips and regions within those, within the timeline that can be looped. And of course, this is a real-time system, so we need to do it in real time, and then hopefully that means wait-free, although Fabian mentioned yesterday we can just use locks everywhere, that's fine. The problem is we're essentially doing file reads, which is a system call, so a potentially blocking operation, so we're going to need some threads in there. So digging down onto this, the typical approach is we have a background thread that will load the files into memory, and then the audio thread will come along and read from that memory. That's how we get the speed. But we can't keep all the files in memory because if we have large files, those multi-hour files, they'll probably be paged to disk at some point. So even though it looks like you're doing a memory read, you'll actually be doing a disk read, and we're back to square one. So the typical approach is to keep track of all the upcoming read positions and then load into memory just sections so everything's nice and hot in cache and we can read it. And you can use memory mapping to help this. It kind of offloads some of the work to the operating system, but it typically works best for non-compressed files where you have a one-to-one mapping between sample position and time. On the other side of things, the audio thread needs to read from this memory, which means we need some hopefully wait-free kind of synchronization around that memory in order to get at the data. And me and Fabian spoke about this in quite a lot of detail on this very stage a few years ago. And if you want even more detail, then Timur gave a 3-hour session on this at CPP Now. So watch the 2-part session from me and Fabian, then Timur's, that's a whole day gone already. So in summary, to kind of work around all these problems, we're probably looking at about 6 months worth of dev if you're quick at it. But again, it's not that simple because, as I mentioned, we have clip or region loop points. So here's a drum sample. Imagine it plays, from start to finish. That's not always the case because it might be positioned with a different start and end on the timeline and an offset, so you don't start playing from the beginning. And of course, it can be looped as well. So you can play from the middle of the file towards the end of the file and then jump back to the middle of the file, which means we have different read positions at the same time. And if you look at the transport, you can see this, same file, 4 different read positions as we're going along. And that probably means we need multiple read buffers, even though we're only playing back one file. And therefore, multiple memory touches if we're doing memory mapping as well. So to figure out this looping concept, probably another couple of weeks worth of dev. Okay, transport position jump in. I mentioned this happens a lot. What does this mean? Well, effectively, when you're playing back, the playhead can randomly jump to a new position. If the user's clicking and editing, then effectively we can just be jumping around randomly. So imagine and therefore the read positions in the files obviously jump. This means that any file caching you're doing into memory needs to be quick because you want to avoid missing samples. If you jump to the start of a bar and then you miss all your kick and snare transients, things are just going to sound a bit weak and not what you expect. So again, there's a few more tricks we need to employ here, perhaps decompressing compressed audio formats so they're quick to seek. Oh, and we also need to work around all those clicks because if you happen to be playing a sample that is, a high number and then you jump to a region where there isn't a high number, you're going to hear that as an audible click. And of course, that's more difficult because you could be playing back a clip that doesn't exist when you move the transport, so you need to remember everything that was playing so you can fade it. How long to work around these? Finger in the air, a month, but honestly, you'll probably spend your life doing these kind of things. Transport position looping. We have global loops in this as well as clip loops. It's similar to just random transport position jump-ins, except that we know when the jump is going to happen and where it's going to jump to. So that gives us some more information, but it might be in the middle of a block. With the user clicking, you can tend to schedule that on a block boundary, but with transport, if you're reading 1,000 samples and the loop end happens to be in the middle, you're probably going to need to chunk that so you don't bleed into the next transient or miss the transients at the start of the loop. And of course, to keep everything in sync, especially with external sources, needs to be accurate. And of course, when we make jumps, our tempo or time signatures might have changed, so any kind of state that's reading audio files need to be updated for that. So another month or so, if we're lucky. Okay, reading files is still not that simple because you probably need to do some time stretching because audio files, they might not be at the same tempo as, I say transport position here because remember we have dynamic tempos and tempos changing all over the place as the things play back. So we're going to need to do this on the fly. Not only can the global tempo change, you might have changing tempos in your file. This can happen if people manually apply dynamic warps for musical or nice effects, but also if you're recording something live that wasn't to a metronome, you can apply a tempo map to it so it plays quantized back with your session. So you've got these kind of two different tempos going on that you need to sync. And of course, that can be looped as well. So you need to deal with those cases. And of course, time stretching needs to be applied quickly without latency. So when things jump around, you get those samples and not either a glitch or missing transients and things like that. So I said another 6 months to do all this time stretching stuff. And believe me, this is difficult. I spent about 6 months recently adding dynamic time stretching on top of all our existing static time stretching stuff. So we had a bunch of things to go on already, and it took a long time. So a quick roundup of how many features we've got out of our big list here. Well, we've got a notion of time and beats. We can read some audio files. Great. It's taken nearly a year to do and a budget of about 100K. Also, there's no UI here, right? We haven't built an application of any sort. We've just built some very small building blocks, some foundation. There's a big list of features still left to do, so let's knock one off. Okay, right. Playback. What do we mean by playback? Well, we've discussed taking samples and converting them to some kind of time or beats, but what we really need is some kind of audio graph that we can build and then hand that off to the device to process. And I'm not going to talk about that in detail because I spent an hour talking about it a couple of years ago when ADC was online. So if you want to look at the finer details and the problems there, certainly watch that talk. How long is this going to take? Well, it took me about a year to do this, but I'd been thinking about it for some time beforehand, and I had our existing graph processing framework, so I knew the good points of that and the bad points that we wanted to replace. And also, it was during lockdown, so there wasn't much else to do. So that took me about a year, so that's another 100K's worth of budget. What are the problems involved, though? Well, it needs to be flexible. These things are going to change over time. You're going to add different types of playback elements, new nodes, so it needs to be able to support that from day one, or you're going to come unstuck. It needs to scale. Your app might be small to start with, only playback a few tracks or a few plugins, but pretty soon the product people are going to say, oh, it'd be great if you could do 1,000 tracks. So it needs to scale well. You need to persist state. That's one of the big things that I was discussed in the talk I just showed, which is when your graph changes, you need to continue playback without any sort of glitches. Add into that latency buffers and things, and it all gets quite complicated. Of course, it needs to work in real time. This is an audio system. And to take advantage of modern hardware, you probably want to be able to process it using multiple threads. And I kind of carried on that talk from Traction Graph into the ADC talk I gave last year, which was how we optimize these systems and make them actually work, really. And I gave a version of that talk at CPP on C, which is a bit faster paced, but has a few nicer examples. So maybe watch that one if you're going to watch one of the two. So another review. We've got the time beats, audio files, and now we've got a playback graph that we can kind of pass to the audio system to play back. But we've still not got any proper notion of arrangement. So what do I mean by arrangement? Well, effectively what we're talking about is a data model. So far, we've just got files and an audio graph that can play them back. But we need to have objects in that model and to be able to specify properties of them. So our objects would be things like clips or regions, and the properties would be start, length, source file, those kind of things. So this is a much higher level concept than a playback graph. It usually maps fairly well to UI if you kind of think of the terms of the properties like start, length, etc. So you've got links to UI from your data model, but also the audio graph needs to be able to build from this. So it kind of needs to be able to read it. You've got two different kind of concerns looking at the model. And finally, the UI will actually usually be built on top of this. What are some of the problems with building a data model? Well, at some point, it's probably going to need to be serialized. You're going to store it either in the cloud or on disk. So you've got to think about file formats, perhaps versioning, backwards compatibility from the off. That's very hard to retrofit. Again, scale as these things grow over time, or people add MPE files with millions of MIDI points of gestures and things. You know, how is that going to be handled? It needs to be expandable. Requirements change over time. Features get added, so you need to be able to support those. Undo, redo is a pretty standard feature these days. Copy, paste, pretty hard to use an app without these kind of things. And also you need to think about how these are going to be shared around. And that often relates to file references with audio. You know, even an external drive, how do you make sure all your resources are still there, and also to friends on different machines. And I talked about data models 6 years ago now at ADC, and the approach we took using juice value trees in Traction Engine. And how long does it take to do that? Well, to do our conversion, I'm saying 6 months here. If you start from the beginning, it took me and Jules about a year to convert Traction Engine, but we had a bunch of features that you might not have if you're starting an app. So yeah, 6 months if you're lucky. Let's put that on the totalizer. Okay, I mentioned the data model needs to, or the playback graph needs to be built from the data model. And we do this in about 2,000 lines of code in Traction Engine. But it's not always straightforward because the way it looks in UI and the way it's played back are often two very different things. Some common problems are things like aux, send and returns, or buses. In the model, they're just bus numbers and positions, you know, pre or post effects. But in the playback graph, they might need to create multiple nodes, perhaps with shared buffers, gains applied to sends, some things together, and all the ordering and latency needs to be handled correctly. Another common problem, track, mute, and solo. So these are just two properties of a track, mute and solo, but they control whether all of the tracks should be audible or not. And what happens if you have things like upstream or downstream tracks when you've got folders, groups, and submixes? How does mute and solo interact with those? And of course, this needs to be highly optimized because it needs to actually work. Imagine places where you have a track that's 2 hours long and you've got hundreds of clips on there. You don't want to process a node for each of those clips. You only want to process the clips that are near the playhead. So thinking about a way to do that appropriately can be complicated. And when you mute or bypass plugins or even tracks, this can be tricky for some reasons I'll talk about a bit later on, but due to latency, you often want to apply your own latency to a plugin as a clean signal so you can bypass it effectively on and off without kind of dropouts or glitches. So there are all these kind of gnarly edges you need to deal with. So let's put some more time on the board for figuring out how to do this. Okay, audio recording. We're moving now. This is kind of the flip side to audio playback, and therefore it's kind of inversed problems. The fundamental problem is that we have real-time audio buffers coming at us, and we want to write these to disk without dropping any. And we have a real-time audio thread that's going to end in a file write, which is going to be a system call, which is potentially blocking. So we need to kind of marshal that system some way. And missed blocks in recorded audio are effectively impossible to recover. You imagine you're recording a live concert that's going to go out on the BBC or something like that, and suddenly you miss a load of blocks recording to disk, you've effectively wasted that entire recording. You'll never get it back. We also need to deal with audio device latency, because if there's latency on the inputs, then when you align things on your timeline to perhaps already existing material, everything needs to line up. And then we have looped or take recordings that we need to do, punch in and out, and make sure everything lines up, and also count-ins usually as well. And at some point, this is probably going to turn into an app with a UI, so we need to think about providing this incoming audio data so it can be thumbnailed. So what are the typical approaches here? Well, we can pre-allocate a bunch of audio buffers that kind of float around, and then the audio thread can pick those up, copy their data into it, and then pass that off to a thread to do some writing. So we're probably going to need some kind of lock-free queue, whether it's single producer, single consumer, or one of the multivariants, which can get pretty hairy pretty quickly, is dependent on your system. But you almost certainly have multiple inputs being recorded at once. So you have multiple inputs perhaps fighting over those buffers to pass them onto the writing thread that's going to flush them to disk. Some of the problems, well, what happens if you run out of pre-allocated blocks? This can happen if your disk writes can't keep up with the audio input rate. Imagine you're recording 64 or 128 channels, and then your desktop operating system decides to do some backup in the background that you didn't know about. You know, how do you handle those situations? What about changing buffer sizes? You've pre-allocated a bunch of blocks at 128, and then someone says, "Oh, this isn't quite working. We'll go to 256," and suddenly none of your buffers fit. When do you reallocate those and supply those to the audio system? Changing channel numbers, a similar problem, but you could have a mono track, you could have a stereo input, you could have a surround input, and what buffers do they use? Do you use multiple cues that have different channels, or do you pre-allocate everything to be 64 channels? That's a big waste of memory, perhaps. Things that you need to think about. Failed file writes. What happens if your disk is becoming full? This is pretty disastrous, but you need to think about how you're going to relay that back to the user so they can act appropriately. Do you need to track disk progress, perhaps preempt how long they're going to record for so you can relay sensible workarounds? How long is that going to take? Again, if you're lucky, 6 months, but you're doing well if you do it in 6 months. Okay, on to MIDI. So we're kind of done with the audio side of things for now, but we've got MIDI, first of all, playback. Now, MIDI is event-based. We have things like note on or off or CC changes, etc. It's not stream-based like audio is, which means we can't reuse anything from the audio pretty much. There is one upside to this in that MIDI tends to be less data. Each MIDI packet is only a few bytes. But there's another disconnect in that in your model, you usually think about things in terms of notes, but when you play them back, they're converted to an event list. And the difference is that notes have a start, a length, a pitch, velocity, channel number, etc., which is where we get the piano roll from. But then when we play them back, we have just a bunch of on-off events. So let's look at the things that can go wrong here. Most MIDI problems are kind of categorized into two. The first of which is missing notes. So imagine you have your transport playing from start to finish. You've passed all the note events. Great. But what happens if you start playing from the middle of a sequence, from here? Now you might think, oh, I can just skip it, but what if it's an 832 bar pad? You might want that to come in straight away. So you need to kind of look into the sequence, scroll back to find any notes that should be on and start them, but also any CC messages because the program might have changed at this point. So you want to make sure your synthesizers actually receive up-to-date CC information so they're doing the right thing. Yeah. And then you can kind of continue playing your sequence. And this may sound like a bit of an edge case, but it can actually happen in loads of situations. If you're undoing or redoing, copy and paste or duplicating notes, the transport is looping around. If you do pitch changes, applying grooves, quantize, swing, all of those things can effectively mean that notes appear underneath the playhead. The other side of things is stuck notes. And you get stuck notes when a note is playing, its note on event has been sent, but then either the playhead jumps or the note has been deleted. And by deleted, that could be its channel numbers changed or its pitches changed as well as actually fully removed. Then you need to figure out when you're going to send the note off for that event. So there's a few situations this can happen. Playhead jumps, so you're playing along and then suddenly the user clicks somewhere else and you're never going to reach that note off event. You need to make sure it gets sent at some point. Looping, very similar to before, we never reach that note off, so we need to make sure we send it before the loop loops around, because otherwise we're going to get that note ringing out and it will interrupt any other notes of the same note number that appear in that sequence. And the big one is a deleted note. So we're at this point playing back, a note gets deleted, and now that note off event just doesn't exist anymore. It's not even in the sequence. So we need to kind of keep an idea of all the notes that are playing and then track these events and then know which notes to turn off at the appropriate time. And of course, this is complicated in a DAW situation because you have multiple MIDI sources. You could have live inputs being combined with playback from clips. You can have multiple clips. You could have multiple tracks being summed together to go into a synth. You can have sends. You can have MIDI generators like ARPs or chords, all generating notes and things. So you have to deal with this in all of these scenarios. So that's easily going to take another 6 months worth of work. Okay, MIDI recording. On the golden path, this is actually pretty straightforward. We have a MIDI thread, which is usually separate to the audio thread, And because MIDI notes are small, we can allocate a large buffer and then write notes into those buffer. And because the MIDI thread isn't your real-time audio thread, it's less time sensitive. There are caveats to this because you still need to get the notes to the audio thread so they can be played back without some huge latency. But for recording purposes, you've got a bit more time. What are some of the problems? Well, what if you're quantizing incoming notes? The note that comes in isn't the note that you actually want to pass on to the audio thread or record. It's a modified version of it. What happens if you want to play back the sequence whilst you're recording it, i.e. live looping? The problem here is that we have a linear stream of events that are coming in effectively second timestamps, and then we need to convert these to beats so they end up at the correct position when they're stamped onto the timeline. Again, another 3 months if you're lucky. MIDI sequencing. This is similar to clip or region arrangement, but what you're doing really is modifying a sequence that is playing back, and therefore all of those stuck and missing notes just rear their head all over the place because you're changing the sequence as it's playing. And of course, you need to add features such as quantization, groove, swing, which is really just a special case of groove, and don't even get me started on MPE because that's a whole other can of worms. So to do some good sequencing, you're probably looking about another 6 months. Let's do another review here. We've got our time beats, we can read and write audio files, we've got our data model, we can save and load our state, we can undo, redo. We've got some hooks for UI, but no UI yet. Remember, this is not an application, it's an engine, or the start of an engine. We've got a playback graph that can read our model and be passed to the audio device, and we can record sequence and playback MIDI. So we've got a few more things to knock off, so let's go quick fire here. Plugin hosting. At some point, someone's going to say, hey, it'd be really cool if we could host plugins. That's all right, because Juice handles all of that for you, right? Well, kind of, but it does the low-end side of things. We still have to think about when to initialize and deinitialize plugins and how to slot them into our audio graph. We have to think about deletion. Plugins often don't like being deleted without having their message loops flushed, so we might need to do that kind of asynchronously. There is precisely one person in the world that understands channel buses, so if you have to deal with those, good luck getting a hold of him. There's state loading and saving. Plugins have state, you save it, right? Well, do you want to be saving or flashing all of your plugin states every time the user presses save or when your autosave timer goes off? Probably not. That's unnecessary work. So you need to track when things have actually changed. And automation, and we'll talk about that in a bit more detail. So to add some plugin hosting, if you're using Juice, perhaps another 3 months. So one of the problems with plugins is they can introduce latency, and therefore we need plugin delay compensations. What effectively happens here is that plugins can lead to offsets in the times that subsequent nodes in your graph are seeing. So we need to compensate for these delays, and I've got a visual I can show in the next slide. But we also need to synchronize the audio that's being heard with audio that's coming in and being recorded. So there's an issue there. And also we need to ensure that plugins are reading the correct automation values once they've been delayed. Otherwise things will kind of drift out of sync. And this is extra complicated when we have aux buses. So to get this kind of thing working, and I'll talk about bypassing in a sec, another 3 months, PDC is hard, and to get it right in all situations is particularly hard. So imagine we've got this example. We've got a drum loop again, it's on a track, and then we've got 2 other tracks. We have it going through an aux send, which is effectively bus number 1. Then that signal goes through a delay plugin. This is really a convolution reverb or a compressor or a limiter. We'll look ahead, something that introduces delay in the signal. And then we have a second track that is taking a return from the first track send, going through another instance of a similar plugin, and then going out to a second bus, and then a third track that is receiving that second bus and then going through another delay, and then the first track is also receiving that second bus and being summed together. Yeah, this sounds contrived, but I've seen these situations from users. And also, we have automation here. So if we build a simplified graph of what happens here, imagine the audio file reads a timestamp of 1. The first 2 delay plugins actually start processing that timestamp, But then when we go through our, the signal is delayed effectively by 1/4 of a second here because it makes the maths easy. And then the second delay plugin delays another 1/4 of a second, and we end up trying to rectify these 0.5 and 0.75 timestamp blocks. So that's not going to work. So what we need to do is introduce another block of latency so everything balances out and we can safely sum those signals together. But remember our friend automation here. Imagine our transport is playing at this position, and this is the value that we send our automation updates to the plugins. That's not going to work for this second delay plugin because, it's not going to work for the second delay plugin because it thinks that the audio it's playing is actually here. So we need to make sure that our timestamps that we're sending automation values for, and also the timestamps that we're sending to the plugins in terms of what the current number of beats and bars is, if they're doing any internal sequencing or beat synced effects, then they need to know that they're not processing what the rest of the graph is processing. And actually, this is a simplified case because Angus brought up in his talk yesterday the fact that you can be looping and this could be the start of your loop. So the fact your second delay plugin here could actually be processing your loop end. So the automation value it's reading isn't really this minus 0.25. It's actually like plus a few seconds or something like that. Okay, at some point, once we've done all of this, we're going to want to render it out to probably a stereo audio file or some MIDI, something like that. But that's a whole headache in itself. We need to detach it from the audio device. We can't be playing something back whilst rendering it. That's not going to work. We need to make sure we flush and reset all of our plugins. We don't want things like delay or reverb tails suddenly appearing at our exports, at the start of our exports. We need to think about what tracks are we going to include. Yes, you're doing a main bounce down, then all of them. But what if you're doing a freeze or a render, something like that? Do you include plugin sidechain inputs? Do you include the outputs of those tracks? What if you have groups, folders, submix? Do you include the destinations in them? What if you've got auxes? Do you include the send tracks? Do you include the output of those send tracks when you're doing these renders? And once you've figured out all of those decisions, you've actually got to do the rendering. You have to deal with audio formats and MIDI, which are very different. You might need to think about different sample rates, different bit depths, normalization, whether you're doing it with peak or RMS, plugin tails. This sounds silly, but you probably want plugin tails if you're doing a render, bouncing track to track or a freeze, but when you're doing an export for a loop, you probably don't want those because you want it to loop around nicely. Do you trim silence? A feature that's often useful for doing podcasts and things like that. What about dithering? How is this going to be resampled in the future? And of course, if anyone plugs in some outboard gear, then you need to think about doing things in real time because faster than real time outboard gear doesn't usually work. So if you're lucky, you could get this done in 3 months. Let's do another quick review then. We've kind of got most of the features now. We've got all of our notion of beats, times, playback, and etc. But we can host plugins and we can export audio. How long has it taken? Well, that's nearly 6 years and nearly £500,000. So quite long. If we look at our high-level feature set, the things based on our user stories, there isn't a direct one-to-one mapping because some of these features are required for multiples of them. But I've kind of broken it down here so you can see the rough weightings. And that's easier to see if we look at it on a pie chart. But the problem here is that all of these are pretty essential. Apart from maybe you don't want MIDI, you certainly want some playback. You need to do your file management. At some point, you're going to export it. There's going to be some element of mixing, sequencing, editing, arrangement. All of these are fundamental features. This is the start of an application. This isn't the end. And of course, there's a whole bunch of stuff missing from this. We've only talked about the engineering tasks here. We haven't talked about any kind of product design, any UI development. We haven't talked about any testing or QA that gets done through the process. Towards the end of this kind of engineering phase, you probably need to build a website, user manuals, and all the stuff that goes into that. And also customer support. You're going to need to train people on what you're building so they can inform other people. So, and again, I feel like I've been pretty generous here. You could easily treble what we've already got to build a product. And now we're looking at nearly 20 years worth of single development and nearly £1.5 million. Now, of course, it wouldn't be one person doing all these. You can throw more people at it. But if you think just in terms of engineering, if you had 5 engineers to this, it doesn't scale linearly. They're not going to do the job in 20% of the time. You need to think about how those communicate, what tools they use, asynchronous working, managers to oversee them. Perhaps you've got more junior people that you need time to support and train. So yeah, it's still going to take a long time. The other thing that's missing, and it wouldn't be an ADC23 talk if I didn't talk about AI, is some kind of artificial intelligence. And I want to talk about artificial intelligence as a tool, not a feature. There are a bunch of features where AI is a particularly good tool. Things like stem separation, vocal or instrument swapping, intelligent mix effects like EQ, compression, mastering, and often mixing needs access to multiple tracks so it can intelligently perform a good job. And then we have our generative AI, such as MIDI, drums, vocals, and even complete pieces of music from text. And these tools or features kind of sit in 2 buckets. You have things that are complementary to DAW workflows, and then the kind of one-button solutions that you just, music from text, say, make me a banging house track, and off it goes. But for most use cases, or I'd say most professional use cases, you probably need all this engine stuff that I've talked about to put your AI tools on top of, right? It probably needs access to your audio files or your audio streams at least to do something. You might need to render down what you're doing in order to pass to the AI-based tools so it can then send something back to you, and you need to reinsert it back into your model. The engine is the starting point here of a product. And Declan, who's the author of the DJ Mag article, kind of summarizes this nicely. He says, artists want to be creative and they want to have control over the creative process. For TikToks or podcast music soundtracks, this throwaway generative music might work, but for artists and producers with their own unique identity, it's hard to see the one-button style solution working. What's more likely is that generative AI replaces steps within the music-making process rather than replacing creativity entirely. And I wholeheartedly agree with this. Now, if I think about things that I could have called this talk, I struggled a bit with what to call it. I could have called it How to Crowbar in as many references of my past talks as possible, which sounds like a joke, but there's actually a serious point here in that I've been building DAWs for about a decade now, and every year I've come across a significantly complex problem or chunk of work that has given me enough to talk about in an ADC talk that other people found interesting, hopefully. So, you know, this is important. I could have called it something very vanilla, like behind the scenes of a DAW engine, because effectively I've just listed all the things that we do. And if you work on a DAW, perhaps you could call it this: how to petition your boss for a pay rise. Yeah. This is hard stuff, and show them this and they might go, oh, you're doing a good job. But let's go back to what I landed on, which was why you shouldn't write a DAW. And perhaps that was a bit misleading. I probably should have called it why you shouldn't write a DAW engine. And that's because perhaps there's another approach. You can use Traction Engine, and yes, this is plug time. I'd like to see other approaches to this, but this is why we've open sourced the engine. And again, if I can get one more talk in there, me and Jules spoke about this a few years ago, quite a few years ago now, wow, at the London Audio Developers Meetup. So let's just look at those costs, because we've been talking about costs a lot today. Imagine you're a company with less than $2 million revenue, which is, you know, standard seed money or early rounds of funding. Our costs are $150 per seat per month. Imagine you have a team of 5 devs, which is not unusual. You're looking, if we take those salaries from before, nearly over $3,500 in salaries. Or you could pay $9,000 in Traction Engine license fees, which is only 2.5% of your wage bill. When you think about it like that, that's a pretty good deal. And also, you get that day one, so you don't have to spend those years of engineering on it. And also, we've spent a long time solving all these problems that I've spoken about, and we haven't stopped. We're still building out features that you can get. One feature that we're adding to Waveform, and therefore the Traction engine very soon, is clip launching. And here's a quick example of what it currently looks like. We're just kind of building out the finishing touches to it. So you could use that. Other options? Well, you could partner with us. We're always open to people with good ideas. Come and talk to us. Me, Jules, Woody are all here at the conference. We'd love to continue our journey with the right people. So I'm going to go back to the quote now from Lex that I opened with. And I'll just reiterate it. If you add the fact that people can't really make any money out of it because it takes so long to develop, you can see why there's no innovation. I think that's actually a big part of it. The economic incentives aren't there. But what if you could take away the fact that it takes a long time? Then you could take away the fact that the economic incentives aren't there. And hopefully what you're left with then is just innovation. And I think that's why you shouldn't write a DAW engine. You should write something new, something innovative. Thanks very much.